we are going to cover number theory, as I said. So today we are covering fundamentals, prime analysis, modular arithmetic, multiplicative functions, and some practice problems. So if I would say the fundamentals are pretty straightforward, as fifth or sixth class student also would know, and next things are much more conceptually hard to get around. So first we are going to learn about divisibility. So what do we mean that A divides B? What do we mean by that? From this we means that there exists an integer C such that B equal to AC. So by this definition we can say that A divides B, and this notation is basically divides notation, which read as A divides B, and its negation is read as A does not divide B. So next we are covering some properties of divisibility, which are that one always divides every integer A. Yes, and negative one too also divide every integer A, and it's obvious that A divides A, and we know that there are two integers. If A divides B and B also divides C, then we say that A divides C. Yes, we can of course say that, because if A divides B, then B equal to A K1. K is some integer which must exist as A divides B, and if B divides C, then C is B K2. And we put the value of B here. C is A K1 K2, and product of two integer is also integer. From by the definition of divides, we can say that A also divides C. And obviously you can scale the number and cancel the number. If A divides then B and A divides C, then A also divides B plus C and A also divides B minus C. It's very obvious. Next we are going to cover division algorithm, which is basically you have any integer A. So any integer A can be written as this form, where B greater than 0 and R is our remainder and Q is our quotient, which is basically long division written in a mathematical form. So when the remainder is 0, we know that B divides A. If remainder is not 0, then we can say B does not divide A. And in our programming, we have integer division and modulo operator. In maths, when you divide mod 3, like percentile 3 is obviously 1, but in C++ and Java, it gives -2. To fix this, just add plus B and then again take the remainder of the number to get the correct output. So next, we are covering fundamental theorem of arithmetic, which basically says that every number, let's say n is any number, natural number, so with can be written as uniquely determined product of primes. Like every n can be written as product of primes, and for every n there exists a unique representation. The theorem says that. So every number can be written as this. So this is called canonical form of numbers, and we can just, yeah. So like 120 can be written as 2 to the power 3 into 3 into 5. So there is not another number which have a same representation as 120, because it's unique. And for every positive integer, nth root of prime number is always irrational. Just it can be used sometimes when we study about continued fractions. That's why I wrote this here. Now, can you all say that is all the things are clear till this point? Are all the things clear at this point? Yeah. So now we are going to cover binary exponentiation. So we know that how to multiply numbers, right? So we have 2 into 3 is 6. But let's say I have to multiply too many numbers, like too many times. So let's say 2 into 3 is 6. We used one operation. Let's not go into the binary internal how many operation it took, but let's say it took one operation. So if you have to do k times multiplication, then the total operations would be big O of k, right? So sometimes like you have, let's say there are queries. Every query has A and B. You have to print A to the power B, right? So there are 10 to the power 5 number of queries, or say 10 to the power 6. And A, B are this. So if you have to compute 2 to the power 10 to the power 9, if we use our previous approach, the normal method we used till now, it would take big O of operations. And this would computationally take 10 seconds, around 10 seconds, which is not a good limit. So to improve this, we are going to use some observation, not say like we are going to use some very big of a deal, but just an observation. What we are going to do is, let's say, I hope everyone knows how to convert a number to its binary form, right? So let's say you have 2 to the power 13, right? So 2 to the power 13 can be written as in binary form, I guess this, if I'm not right. Yeah, this. So 13 can be written as 2 to the power 3 plus, oh sorry, this. This is just a binary representation of 13. So we have to compute 2 to the power 13. What we are going to do, return this form at here. By doing that, what is beneficial? Like you get to see the pattern. 2 to the power, 2 to the power 3 plus, yeah. If we write this, so what exactly come into our brain? Like we need to just, if we are this step, you are at 2. If we, like you have string of binary, we are at ith step. Ith step is also basically ith index of the string coming from backwards. So you will be multiplying 2 to the power I always. When you have to apply, when the bit here is set. So we are going to use this as a base as in our algorithm. So you have to compute x to the power n. So obviously we know that x to the power 0 is obviously 1 for x not equal to 0. Sorry. For x not equal to 0. And at every step, we have to square our answer. Because you need 2 to the power I power at the ith step, right? As we saw here. At ith step, we need 2 to the power ith power. So we keep squaring to get at every step we square. So let's see its code. It's better to just look at code and realize how it actually works. So you have first, let's say at iterative version, you have function and you have base 1. Because at 0th step, 2 to the power I is 2 to the power 0, which is 1, right? So while n is not 0, your while loop is going to run. If n is odd. What does that mean? If n is odd, that means the bit at that position is set, right? I hope this is very understandable. Uh, that's why we multiplied by a in our answer. Else, what we did is we have our variable a, we square it, and half the n by 1, half the n. It's bit shifting. I'm right shift, I guess. I don't know. I'm just confused in left or right. So, and we return the answer. So, if you want, I can explain it through the example too. How are we calculating x to the power n? Do you guys understood, or do you need example?
Sir, please show example.
Yeah, sure. Uh, so let's say you have to compute 2 to the power 3 to the power 13. So you have our answer, which is going to be a final answer. Okay. So 3 can be written as yeah, 3 can be written as this form, right? So while your n is 0, what is n? N is here 13. N is odd. So what we are going to do, as it's odd, you can see the bit here is 1, right? At 0th step, when you go here, the bit here is 1. So we have answer as base equal to 1. It's 1 because x to the power 0 is 1. So we multiply the answer by a. So the answer r becomes 3. Then our a, that the power we are going to multiply, which is 2 to the power I, is a, which is that squares. So next step, we see that 13 by 2 is 6. At next step, it's 6. Our n is 6. So at 0, as 6 is even. So we are going to just cannot, since the bit is 0, we cannot directly multiply the our squared number, the 2 to the power I, to our answer, because here bit is the contribution of 2 to the power 1 is no contribution. That's why we are going to skip, and 6 by 2 is 3. So 3 is odd. So we have 2 to the power this, and we multiply this, and whenever the n is odd, we are going to multiply that to our answer. So this is basically the binary exponentiation. But why are we using the binary exponentiation? Because the earlier thing I said, that we are going to getting big O of n complexity per query, as there are 10 to the power 5 queries, and this big O of this. We are going to get big O of b query. So every time we are halving our b, which means that b goes to b by 2, then b by 4, then b by 8, b by 16. How many steps are there? There are obviously log n steps. So for per query, log b steps, sorry. So for per query, you are optimize your solution from linear time to logarithmic time. So for every query, you have big O of log b, and your complexity would be like 10 to power 9 log b would be 30 something. So 30 into, so total complexity would be q into log b, which is that is easily can be passed in under 1 second constraint. Is the things clear about the binary exponentiation? Yeah. So uh, let's move to another topic, which is Euclidean algorithm. So A and B are two integers which are not zero. You need to compute the GCD of A and B. We are going to discuss how are we going to compute the GCD of these numbers. First, let me introduce what exactly is GCD. So GCD is the biggest number, let's say G, that divides A and also divides B at the same time. So it's a definition of GCD. So GCD has a very peculiar property, which is GCD of AB. This is a notation used for GCD basically, or sometimes people use it like this, but we are going to use it like this. So GCD of AB is equals to B A mod B. So why is this thing true? It's true because of the fact we studied the if A divides B and A also divides C, then A divides B plus C and A divides B minus C. So basically, if we do this every time, we are going to get the GCD of our numbers A and B. How are we going to do this? We need to have some stopping condition. The stopping condition is when the remainder is 0. Then we know that this number that B divides A. This means that B divides A. That must be a largest number. Then we can say the GCD of A and B is B. The complexity would be big of log min of A and B, because x mod y is always less than x by 2. So the properties of GCD are symmetricity, obviously, and Euclidean property, of course, because we show that A, because of this, we can say that for every integer, we can subtract A. So if we multiply the two numbers A and B, the GCD also we multiplied by K. The co-prime numbers are basically numbers A and B, which are does not share a common factor else than 1. So there is Wizard identity, or sometimes people say Wizard lemma. This says that A and B belongs to integers, obviously, and GCD of AB if equals to AX plus BY, then there must exist two integers, a pair, such that this equation satisfy. The Bezos lemma says that. And there is another quantity called LCM, which is least common multiple. Uh, so that is a number D, such that A also divides D and B also divides D, and D is minimum. So that is called LCM, and GCD into LCM equals A into B, product of numbers. So there is a problem on code forces. This we can cover. let's first see the how do we code the GCD out. So it's very simple. As whenever b goes to 0, return a, else return GCD b and a mod b, as this is exactly written this property, like it's a 1 or 2 line code. So we are going to cover one problem on this. Is the GCD clear, by the way?
Yes, sir.
Yeah. Yeah, sure. Let's. I hope you all guys read the problem. Oh, so anybody thinking of anything? It's going to be the things that we only covered till now. Anybody want to share their approach?
I think we need to find first the GCD of A2 minus A1, A3 minus A1, so on till AN minus A1. And then for each iterative column, we have to find the GCD of A1 plus BJ. And then we have to take the GCD of both those numbers for each row. And that's how we get the answers for each row.
Yeah, exactly. Yeah, that's just yeah. Basically, I don't know who it was. Can you? What is your name?
This is Sahil Bansal.
Yeah, Sahil. As Sahil stated, it's correct. So I hope it's correct. So I hope all of you read the question, right? You are given an array A, an array B. So you need to print GCD of A1 plus BJ, AN till BJ, such for all J. Yes. So here, the first thing we would notice is that the GCD has the internal term has a very common thing, right? Which is BJ. So if we remove this step, like the brute force approach would be n square, right? If you just go to every j and calculate GCD, and that would be going to get a TLE and the log of GCD2. So we are going to use this Euclidean thing that uh, the GCD of A and B is GCD of A, B minus A. As Euclidean property states that B minus KA. So we put K as 1 here. So let's say this quantity is P. So P is GCD of, if we apply this, and this property also applies to many numbers too. So A1 plus Bj is A2 plus Bj minus A1 plus Bj, and so on till An plus Bj minus A1 plus Bj. So P is just GCD of A1 plus Bj and A2 minus A1 till An minus A1. So it's the problem was made a quite lot simpler, right? So if we conclude the GCD of this, we can get the GCD of this by using only one operation, which would be log of max of, oh sorry, min of this value. Let's say this is G1 and A1 plus Bj. So for per query, we are getting this time complexity. For query, I mean is for per j. Right. So we just compute the value. P is GCD of A1 plus BJ and G1. You need to compute just that. I hope the problem is clear. Should I move forward? Yeah. So again, we goes to Bezos identity, which says that a valid pair x comma y is definitely going to exist for this equation. So this is extended Euclidean algorithm, which is just representing GCD in terms of A and B to get our x and y, right? So the complexity of finding x and y would also be similar to finding the GCD of numbers, which would be also logarithmic. So what you have here is you start with base case b is as 0, right? And GCD of x and 0 is x. So GCD of a and 0 is a. So we put the values and we get our initial solution, which is x0 and x y0. So as we know that how can we represent the remainder? It can be represented as this a minus a divided by b seal into b. And since we were doing this, right? So now you have to find the value ax by GCD of a percentile b, right? First, like what we actually did here is that you have a solution equation this, right? So if we start with, so if you think from backwards point of view, if the value of b is 0, how are we getting our x and y, right? So that is why it's a base case. So we are finding solution when this is right. So when this is, we have a solution, but we have a solution is x as 1 and y as 0. And we recursively update by this, because here exactly what we did is finding this. We goes from a to b to the a and 0, right? Now here we are finding solution for this and then going from this. It's just a backward thing. I hope it's just a this thing. You can use that template anywhere. I hope this is clear. Uh, should I move forward?
Sir, what if A and B are 2, 3, and then the GCD is 1, then how do we express it in terms of 2, 3?
Like 2x plus 3y is this, like this.
Yes, so GCD 2, 3 is 1.
Yeah.
So like for x and y will not get natural values.
Yeah, I'm saying that x and y belongs to integers, not natural.
Okay.
Yeah, it would be 2 and negative 1 for that one. So you have, I'll upload this PDF in the group and you get to click on this problem homework. I can't because I'm editing the PDF. You'll when you click on it, you get redirected to the link. But anyway, now basically the fundamentals you need to know are over. Now we are going to study how are we going to factor a number computationally in good time. Computationally acceptable time is more better word. So let's start. How are we going to factor our number? First, we need to know what is a factor of a number. A factor of a number is a number that divides that number. Let's say D is any number and n is any number, you can say D is factor of n if and only if D divides n. Yeah. So it's the factor. Now, if you think about it, there are very big n's, and sometimes we need to have a use of their factors. Let's say you have a problem, you are asked to give the list of all the divisors, all the factors of n. So how are we going to do it? So the basic naive approach would be just to iterate from 1 to n and check if n divides, I divides n, then add that I to our list, right? But that would be very naive way. There exists a better way if you just think about some common observation. Let's say you have two factors of a number n. Let's say you have n, and there are two factors, f1 and f2. So f1 into f2 should be less than equal to n, right? So we can say that if both of the, like, we are finding the upper bound for the fi. So if both of the factor are greater than root n, then the product would be root n, like f1, then f1 f2 is, oh sorry, which would be contradiction. So here we can say is every factor is strictly less than equal to root n, right? So if every factor is less than equal to root n, then why should we scan till from root n to n, right? Why should we do that? So our approach would be that if we found a factor less than equal to f, then the other factor would be n by f1, that is f2.
So we cannot say that both the factors are less than root n, but at least one of them has to be.
Yeah. Sorry, I wrote and here, right? Like, if the I just showed it by contradiction. If both are greater than root n, then the product would be greater than n, which is impossible, and you can't have those factors. So we need to scan till 1 and root n. Yeah. So here is a code of how to calculate the factors. You have a function, you initialize array, just check from d from 1 to, if d square is less than n, increment your d. If it's divided by n, oh sorry, if the remainder is 0, then it's obviously a divisor by the definition of divisor. And if you need to push this to our factor 2, because n by d is also a factor, and we are not going to scan after this. And there is some exception if the number is perfect square, like 5 is a factor, and here 25 by 5 is also 5. So we are not going to push that in our array. Or you can use just set here. You don't even need this condition, just push back this. Yeah. So now we are going to covering sieve of Eratosthenes. My pronunciation of that word is bad, so I always say it sieve. I know there are other algorithms like sieve of Atkins and sieve of other something also, but we mostly use sieve of this, so I just use sieve. So we need to find a better method to calculate the factors of a number, right? Like print the uh, list of factors of a number per query. So if the number of queries are this or this, let's say this, uh, for this, you have a time complexity of big of root n, because we are only scanning till 1 to this range, right? So it's big of root n, and for per query you are going to use this, and your total complexity would be this. And let's say the n is also 10 to power 6, so that would be 10 to power 9 as a whole, and which is not acceptable in most judges. Like how C works, like when you know that 2 is a prime number, then multiples of 2 are definitely not the prime number, right? So what we are going to do, we maintain an array of initially true all. Let's say like where true represents that you have that the ith number is prime number. So first we go to 2. 2 is obviously prime, we know. So as we move forward to the multiples of those primes, right? So we're going to mark it as false because that number is definitely not prime, right? And we as we move forward and check if uh, value of that is false, then we just move forward. And if the value is true, that means you found the prime number. It's just as simple as this. Because if it's not a prime, then it should have a multiple before from the other primes less than that number, right? So that must be a prime. So every single left out number is a prime number. So here is a simple code of a sieve. You maintain, you initialize array and put true values all here. So you know 0 and 1 are not prime, so you put false here. So you go from 1 to n and check if the it's prime. Uh, it's not prime, then continue, else primes, then push the value I to the prime because it is a prime. And this loop does is mark the multiples of the number we currently find out as false. So we have number n. So you have n. How many multiples of 2 are there till this? There are only obviously n by 2 multiples, and for 3 there are n by 3 multiples. So you have this p less than equal to n 1 by p. This amount, total amount your loops are doing work, right? So this is your complexity of your sieve. From sieve, what we got is all the primes till 1 to n, right? So as a very well known result that this is big log of n. So as here, obviously n is multiple because you are doing this here. So the total amount of computation you done is n log of n, and you used your array to maintain whether the ith number is prime or not. That is space complexity would be big O of n. So let's have a practice problem. You are given a two integers n and q. For each query, you need to print how many integers have k distinct prime factors. I'll give 2 or 3 minutes to just think how are we going to approach this. Then I'll explain the solution. Yeah, if anyone gets the idea, just speak to me. Here you have q number of queries, and till n you have to print count of integers in range having exactly k distinct prime factors. Does anyone have an idea how to solve this? Yeah, let's discuss the solution. How are we going to approach this problem? So we have q queries, and every time you have to print the count of integers. You need to print count of I such that I has k distinct prime factors. Like I should be having this kind of representation, right? So if you realize that, let's say n is 10 to 1 7, so by using sieve, what we have just learned, we get the primes, right? So
The
we
GCD of
were here.
A1 plus
Instead of
BJ, and
doing
then we
is
have to
prime
take the GCD
as
of both.
false, if we just maintain a vector of or the set for every index, uh, then just add the I on that, we'll get the, then at the end we iterate through the is prime array and get our length of that set. That means that number has k distinct primes that has visited it, because this loop is visited by the basic prime, right? If the number is prime, then this loop starts. So then make a hash map of it, then you can print the answer in a big O of 1 per every query. Is the solution clear? C is also a factor, and we are not going to scan up. Yeah, I hope so it's clear, because there was nothing here. So there is also a method faster than root of n, but it takes a pre-processing of the primes using C. So first we were doing is calculating the factors of number in this time, right? So if we have factorization queries, it becomes too slow. So to factorize n, by using sieve, we can just append the smallest prime for every number. Like a number is make it's a visited, or like normally, let if I divides p, then it then P is the smallest, like you are going through the loop, right, for I to N, right? So if for P, I divides P, right? So we will know that it's gonna be the smallest prime factor of that number because you are going in a ascending order, right? Or it's just basically this. So we create a SPF array, and for SPF uh, denotes is a S, I mean smallest prime factor of n I. Sorry, it can be done using sieve by pre-processing and then this. So you do the SPF array, initialize it, then uh, iterate from 1 to n. Then initially SPF of I is I, as we don't know ith number smallest is divided by I itself, so we have no option rather than this to choose as we don't have information of I. So we go till the primes, right? So here you, you are iterating through primes p2 p square less than max n, which would be n. So if SPF of is not equal to p, that means it's obviously computed already. You don't need to uh, do it again. Then you have nested loop for which we go through the multiple of it is like if first number is SPF of j is p, then we're going to mark it as p because it's a first time visited by the prime p. Then we go to the factors, then you divide simultaneously n by SPF of n, then the number you get is again do this, you get all the factors of a number. So the complexity would be big O of this as we pre-process, and it's basically sieve too. And since we are dividing n by SPF of n, SPS the lowest value would be 2, so the worst case complexity would be log n. So it takes log n time complexity to factor a number per query. Now, is this things clear? Oh, sure. If anyone has any doubt, you can just speak. Yeah, so let's cover linear sieve. What is linear sieve? The linear sieve is finding this more better, like you will get a SPF better. and with a better complexity. So when you are doing a normal C, you are doing the computation again and again for, let's say you have a number 15. So 15 is visited by a prime 3, right? Because 3 cross 5 is 15. And when you have a prime 5, then 15 is also visited by it, as 5 cross 3 is 15 too. So we are getting the useless operations by going to higher prime, right? So by using linear say, we are going to stop at a smallest prime factor only, and then we won't go again. I mean ahead. So here is a code very similar to C. So you go 0 and 1 are obviously false because they are not prime. If it's a prime, then push it to primes. If it then for primes, if p cross I is greater than n, then I cannot be anything. So uh, is prime I cross p is obviously false as it's a multiple of prime. And if I divides p, then you need to stop here because a number can be written as, right, this p1 to the power a1, p2 to the power a2, 2p to the power ak. So you have ith number. So it's going to be visited by primes, right? So the first prime that divides this is obviously going to the smallest prime that this number n divides. So we are going to stop at this. So obviously that is going to be the number which is no also are not prime. So here after breaking here we redundantly reduce many steps of as 15 as an example as I discussed. So the complexity would be big of n because every number is visited at most one, right? So that's why the complexity of it is big O of n, and space complexity would be big O of n to store the whether the number is prime or not. So we have a problem. So you have a number n given in input, and you need to find a unique ordered pair x and y such that x plus y is n and GCD of x and y is 1. Does anybody have an idea how do we solve this? Like x plus y is n and GCD of x and y is 1. So I guess there's no one who knows how to approach this. So it's only a hidden thing to taken care of because x plus y is n and GCD of x and y is 1. So y is n minus x. So GCD of x and n minus x is 1. And we know that the property GCD of A, B, GCD A and B minus A is equivalent. So we can write this as GCD of X and N equals N, and similarly GCD of Y and N equals N. So you need to just count the numbers such that it's co-prime to N, which is calculated using Euler-Tauschent function. Uh, this is just a hidden way to represent a Euler-Tauschent function, like x plus y is n and GCD 1. So what is a Euler-Tauschent function? Euler-Tauschent function is a function that counts the number of co-prime integers in range 1 to n such that their GCD is 1 or say co-prime. So you have a number n. It can be written in this form. So its Euler-Tauschent function is this. Let's not worry about that. We are going to prove how did we get this. So you know that what what would be the Euler-Tauschent function of prime? Like a number which is prime, then how many numbers are in range 1 to n such that GCD of I is in this. Obviously, there are going to be p minus 1 numbers, like sorry, p here. So there are p minus 1 numbers as p divides p. This is the only number that is not co-prime with p. So phi of p is p minus 1. But if we scale the power of a prime, right? Like, how do we calculate phi of p to the power k? Like, how many total numbers we have? We have total numbers p to the power k, right? So, how many of them are not co-prime with p to the power k? Obviously, that the numbers which have a p as a common prime factor, that is going to be the numbers which are not going to give a GCD at least p. The GCD can be p square, p cube, but if we just go to the p, we are going to count all of those numbers. So how many numbers are there that going to give GCD as p till 1 to p to the power k? That is going to be, which is p to the power k negative 1. So you know that if two numbers are co-prime, then phi of a dot b is phi of a and phi of b. We are going to exploit this to derive this. So how are we going to do this stuff? So you are given n and speed. So So as we discussed, obviously phi of p1 to the power a1 is always co-prime with other powers or other primes, right? So we can just write this as p1 power a1 into phi of this, and we use this again, then at the end we are going to get this, right? So as we calculated, our Euler-Torsson function for prime to the power k is this. So phi of n is just p a1 minus 1, this till p to the power ak. So phi of n is, if we take common p to the power a1, then it's just, then it is, and just this. So phi of n would be, this number is very familiar to us, that is n is this. So we derived how to calculate the numbers that are co-prime to n, from 1 to n. So here is a code of Euler-Torsson. How do we calculate this? As a base case, phi of 1 is 1, and it's based on how this works. So you go from 2 to n. If the number is prime, you're going to push it to primes, and phi of p is, obviously we know, is this. So we did exactly this. So for p in primes, uh, we just use the linear sieve method. So phi of I into prime, as p is a number that have GCD 1 with I, then you can say that phi of I into p, right? As it's a prime. There is no need to have a GCD of 1, right? Then else, if the GCD is 1, then we can write as this, phi of p is p minus 1, this. We just use these things here. So in big O of n, using linear sieve, we find out all the count of phi I for I to 1 to n. Yes. So I think that is enough for today.